drives a spinning pinwheel. Can you see that? The message there is that we got an internal source that is sort of driving something towards the exterior. Okay?
Yeah.
And for the bottom diagram, what you see is just like an explanation of that mantle convection we're talking about. You put up a fire at the bottom of that cylinder, and then what that does is that it drives hot magma, if you like, okay, upward. Why does it drive it upward? As you can imagine, it's hot, it's light, it means it's going to be buoyant, okay?
Yeah.
And then because of that, it rises. It rises to some certain extent. As it does rise, what happens?
The
It gets
one.
to some point, it cools, increases in density, and falls back down. Those two processes result in some sort of convective cells that begins to develop a pattern, right? That is cycling, okay? And that is what sort of drives that internal heat engine. Do you understand that?
Yes.
Okay? That process alone will result in volcanoes and earthquakes. So the internal heat engine drives volcanoes and earthquakes, and that those are different topics. Oh,
Yeah.
mountain building process.
Like,
So that is the internal engine, right? What about the external?
yeah.
So you told me that you did some work on weathering, erosion, transportation, and what deposition, right? Yes or no?
Yeah.
What drives that?
Mm.
What drives that?
Like changes in the external conditions.
From someone, e.g., wind, water, glacier, gravity. Being facting, those are the factors that will drive weathering to some extent, right? But what leads to those factors
They're
is
like
the
the.
external heat engine we're talking about.
Mm.
Now,
Okay.
the sun, the sun drives all of those processes.
Interesting.
Those five or four processes we talked about, those are chiefly driven by the sun, okay? Because we know that the sun drives atmospheric and oceanic circulation. Do you know how that works?
No.
Do you know how that works? The air you have outside is made up of tiny particles called air parcels. All right. Now, when you have sun, right, what happens is that they develop a hot air parcel, okay, that rises because of again with buoyancy. It rises to some certain extent, okay, get to condensation levels, get saturated, and that's the black sky you see, and then you begin to have rain. Are you who's with me here now? Have I lost you?
Yes, sir.
Have I lost you?
Yes.
The question is how do you have rain? How do you get rain to fall? Rain will only fall when you have hot air rising from the ground to some sort of level called the condensation level, lifting condensation level, LCR. Above that level, right, the air gets saturated, and that's when you begin to form cloud, all sorts of cloud, right? And then when you form those clouds, okay, you begin to have tiny droplets that correlates to form raindrops that comes back to land. That is what now drives weathering. What is weathering? The disintegration of rocks to get tiny particles. Those particles get transported and deposited elsewhere to form sediments. Okay?
Yes, sir.
So, that is the atmospheric process we talked about. So you see that most of the concepts in geology are driven by this internal heat engine we talked about, and then the external heat engine from the sun, primarily from the sun. Okay? If you look at the oceans, okay, when we talk about oceanic circulation, deep down, okay, you have a conveyor belt, okay, hot water, cold water. Those are so you see all of the oceans in the world, they are kind of interrelated. Okay, and then there's a circulation pattern that goes on and on. Okay, from cold oceans to warm oceans. Okay, that pattern cannot could be disrupted but shouldn't be disrupted. Okay, now let's take true to the nose because the key point is about these two key driving processes. So remember one of those questions I asked you? What is distinguished between what? The internal and the external engine.
And the
And
process.
what was the last part? The processes. Okay. So look at the title of this slide. Powering the earth. You already know the earth is made up of four systems, which you mentioned. And then we know that these systems are driven by two sources, both the internal heat engine and then the external heat engine. Is someone learning something today?
Yes,
Are we on the same page?
yes,
Alright. Can I move on?
yes,
Okay. We've talked about this before, the divisions of the earth in terms of composition. We said you've got the crust, the mantle, and the core. The crust could be oceanic or it could be what? Continental.
continental,
In terms of density, which is denser?
oceanic
The
crust.
oceanic crust is denser, and because of that, you only find oceanic crust underwater.
Hmm.
And for continental crust, because it is lighter, you're going to find it above water. And that brings us to the principle of isostasis, where these materials will try to reach equilibrium. We'll talk about it in a bit. Okay?
Yes, sir.
So the mantle is hot, solid, and flows slowly over time. Okay? Of course, on the right hand side of the slide, what you see are figures, right, that are self explanatory. And then you've got the core that's made up of what? The outer core and the inner core. The outer core, right, is the source of the Earth's magnetic field. Are you aware of that?
Yes,
All
sir.
right. Why?
Because
Why is it the source of the Earth's
because it is liquid and it contains iron and nickel.
If you're talking to me, come on, talk with some confidence. Come on
I
now.
said because it is liquid.
Liquid?
Yes,
Yes.
and it contains iron and nickel, and the convection of that iron and nickel creates a magnetic field around the Earth.
So you know it's why you not. Who taught you that one?
I believe it was you.
Was it me?
Yeah, you're part of that purpose.
When?
GUI 102 and in geophysics too.
But I'm impressed with that answer. So not only of the fact that the material flows, it has metallic material minerals that scales several times, right, than the mantle material. Right? That's why it's generated from the mantle materials are not made up of iron. Alright? They are majorly made up of silicate minerals. That is why the Earth's magnetic field is not generated from the mantle. I want to say okay.
Yes, sir.
Alright. So I'm done with that slide, right? Slide 7 now. Remember, I talked about divisions of the earth in terms of composition and what?
Geology.
Rheology. So another name for that could be what? Mechanical
Mechanical.
or strength. Okay? And in that regard, what we have is that you have two types of material: brittle material or ductile material. Okay? So the lithosphere is brittle, has more strength compared to the asthenosphere that is motile or ductile. Okay? So the asthenosphere behaves as though it's plastic. And that is why the lithosphere is able to float on top of the asthenosphere. All right. Now, slide 8 or 9 is titled Continental Drift. So what we want to do is just to dwell on some of the processes that will take place. So on here, what we want to talk about is plate tectonics. Okay? And we've already defined the theory of plate tectonics, right?
Yes.
Now the question is, how does plate tectonics work? You already said the earth is broken up into blocks or plates, lithospheric plates. At least 7 lithospheric plates. But what is the driver? Do you know?
Mantle
Convection.
convection.
Mantle
Mantle
convection.
convection, ridge pull, slab flow.
Okay.
That's the three now.
Who taught you that again? Me?
No, the back or
But the two main concepts here for plate tectonics is number one, continental drift, and number two, seafloor spreading.
uh,
Okay?
yes, sir.
The theory of continental drift was brought forward by a guy, a German meteorologist in 1912 called Alfred. Okay? And his theory basically was that, the Earth, again, is broken down into plates that are constantly in motion, right? And that number one was the fact that the continents need to fit as a jigsaw puzzle. Because if you look at the coastlines of Africa and South America, you will see that you can basically fit them together, including other continents. He also brought out fossil evidence, all right, where he talked about fossil evidence such as Glossatoris and Mesosaurus that they can be found in different continents. Okay, and the fact that you can correlate all of these fossils across this continent, it meant that in time past, these continents were once together. Okay, and he also brought, evidences like paleoclimates. Okay, saying that some deposits you see today are not in fact suggestive of the locations where you find these deposits. For instance, coal, for instance, you find some coal in polar regions. Coal would not form in polar regions. Coal will form in tropical regions where you have dead plants die and get buried. Okay? The fact that you find those sort of deposits in areas where does not suggest they originated means that those continents are drifted. However, he did not come up with a clear-cut evidence for why continents drifted. Okay? And then American geologists at that time debunked the theory of continental. Not until after World War II that they began to relate with the theory of continental, where we now had available other evidences to back up the theory of plate tectonics. So he had insufficient evidence were found for driving mechanism, and his hypothesis at that time was rejected. So the theory of plate tectonics talks about broken plates that are constantly in motion, and that explains volcanoes, earthquakes, and mountain building processes. Okay. After World War II, it then gained, after a lot of evidence, it then gained significant support. And I think that theory was finally established in the 1960s. But we're not getting tired. Don't lose sight of the point I'm trying to drive at. We're talking about internal processes and external processes as those shape the land surface we see today. Now, slide 11. Having talked about the theory of plate tectonics, okay, and let's assume that it was established then, right? because I'm not showing you on the screen. On slide 11 shows us the types of boundaries we have. We have the divergent boundary and how that originates from rising magma. Okay, you have three sets of diagram there. And then we further rise, and in fact, with the regional stresses, extensional in this case, driving further. So all of this emanates from what? Conventional, mountain convection current. We talked about that already, right?
Yes, sir.
We said rising magma due to buoyancy gets up beneath the asthenosphere, causes some sort of pressure, and someone mentioned the name just now. Ridge what?
Reach push.
Ridge push. Ridge push. Gets up, pushes it, okay? Gets cold, sinks back. That's the driving force for divergent boundaries. Divergent boundaries. And at the end of the day, what you have is the development of a new ocean. Have you heard of Wilson cycle?
No,
The
sir.
Wilson cycle. The
No, sir.
Wilson cycle talks about the opening and closing of oceans. And that is driven by these tectonic forces we're talking about. So it leads to the opening of a new ocean, divergent boundary, okay? And then for convergent boundary, where you have slab pool, okay, you can have three types of scenarios. The first one is that, of course, you know we've got different types of lithospheric plates, right?
Yes, sir.
Oceanic, continental, right? Two types, I should say. But in terms of the movement and boundaries, there could be three types of movement. It could be oceanic continental, converging, all right? And in that case, the denser plate will subduct, all right? And then you can have oceanic, okay, where there's no subduction. No, actually there's subduction, but the older oceanic plate will subduct. And then continental, where you have no subduction. Instead, what you have is the creation of mountains. For instance, Himalaya mountains in Asia. Okay? What are these people? Are you for this class? Why are you just coming? Yeah, what? You had a class. What class was that? Are you in 200 level? What about those guys behind you? Well, that boy. You know. Okay. The other thing I need to say about these three scenarios is that you've got different. Look at those people. I said you are kind of you are watching your phone. You have to do that boy on the like after camp. I'm a Chelsea fan, but I will send you outside. When you concentrate, this might be the only time you have to understand what I'm saying. Because of the struggles of life, you might not have time.
Deep.
But once you listen up and you understand this from here, then you don't have to spend too much time reading it again. Or you don't like my explanation?
Oh, we love it.
You don't like it, right? I'm talking to you all now. This man, what are you watching? Video back home. That one. Is it bright for you now?
Ah,
I will continue. What am I talking about? The entire heat engine is driving plate tectonics. Can you relate?
yes, sir. Yes, sir.
All from mountain convention, right? That's how you get that ridge push, slab pull, all right? But without convention, it's impossible to have plates drift. Are we on the same page?
Yes, sir.
Now, before the distraction, we are talking about three scenarios for convergent boundaries. And we said that these three scenarios could lead to a variety of superficial features.
Mm.
For instance, if you look at slide 13, oceanic continental collision. Are you there? What you see is that you develop on the surface.
Okay, okay. Even on PPT. Same thing.
The problem with you guys is that
It's the same thing on
you are not tech savvy. You are a Gen Z generation that is not tech savvy. The only thing that most of you know is how to
Oh,
bomb.
okay, okay, okay.
When it comes to technology like this, you are not, it's not showing you. It's not showing you. It's not showing you because you're using your phone. Your phone does not
Still
support
recording.
MS Word. Okay? You see, for instance, the Himalaya mountains. That's about some of the highest peaks of the world today. Okay? That has to do because of the type of continents that the lithosphere that are converging. Okay? Alright. So the last type of plate boundary is the transform boundary.
Like game and
Who is playing what there? He's playing music. And this you already know. These are places that slide past each other, right?
yeah, that
And
one.
these are quite important because without transform boundaries, we wouldn't have known the difference between a transform fault and a true going fault. Okay? Example of this is the St. Andrews Fault along the west coast of the North American continent. Okay? I'll leave that for now because we're not dealing with that. But in all of this, if you go back from the transform boundary slide, right? Go backward, continental collision, oceanic collision, and oceanic continental collision, you will see that the surface features are distant. Yes or no?
Surface features are what?
Distant.
This.
They are
I don't know.
different.
Oh, this thing. Yeah. Oh, okay.
No one of these scenarios gives us the same superficial features. Are we still together?
Yes, sir.
Now, we can safely say that all of these features are driven by what? By what?
Electronic.
By what?
Electronic.
I don't know I don't
Plate
know.
movements, Abi.
The internal heat
Okay,
engine,
electronic.
right? In the form of what? Man to what? Convection. All right? Good. Now go to the next slide. On that next slide, okay, you now have what we call sufficient processes. The external heat engine. So the internal heat engine gave us all of these features that we see on the surface, right? But it doesn't end there. So internal heat engine, right, drives nicely into plate tectonics. Plate tectonics gives us all of these arcs, mountains, flats, tops, and all of this. Okay? Now, all of these sufficient features are then further worked on by the external heat engine, which is driven by what? The sun, the solar system, solar radiation, I should say. Okay? And then that feeds back into the present day configuration we have. Okay? So you have isostatic adjustment and uplift,
Yeah.
okay, as one of the superficial processes. And when you talk about isostatic readjustment, what happens is that as you begin to weather and erode stuff, okay, the land, okay, will always want to readjust itself. Okay? Taking off some of those. So think about it this way. But I don't think anyone has entered the ship here before. Have you entered the ship? The ship? Who's gone on the ship? What I'm trying to make, the lighter the ship, the higher it will be on
Yeah.
water. The more cargo you have in the ship, the lower it is, right? So the more stuff you take off the ship, it will try to readjust itself to normalcy. And that's what isostatic readjustment or adjustment is all about. Okay? The weather, the land will try to pull up itself. Okay? So removal of material by erosion allows for what? Isostatic uplift of underlying rocks. And then we talked about weathering and erosion. I don't need to dwell on that. We've got all of the agents of weathering that are driven by the sun. Okay?
Yeah, yeah.
Land, I mean, rainfall is driven by sun. The same process that drives rain is what drives snow. The only difference between the rain and the snow is that rain will occur most especially around the tropics, but snow will occur at higher latitudes because that determines so the temperature of the cloud, all right, will determine what's going to fall back. So in the tropics, you're going to have cold clouds, and then instead of ice drops, you have ice pellets. That's what collates to form snow, snowflakes. But because we're in the tropics, we never will find snow because we never have cold clouds. What we have is warm clouds. So what you develop here will be raindrops, raindrops, and that's why we have the enormous amount of rain we have today. Now, deposition. So all of these are surface processes. Weathering and erosion and static adjustment, and then deposition of those sediments that have been weathered and transported elsewhere. Okay? And then that's how sedimentary rocks form. Because you begin to form these deposits from these sediments from the weathering, erosion, and then the deposition. When they are deposited, they don't just form sedimentary rocks. They undergo what kind of process? Say again? Diagenesis. Diagenesis? I don't know about that.
What's the question?
Sediment to device materials.
Okay. I'm learning that for the first time.
Yeah.
What I was expecting was lithification.
I feel on
I don't know. You guys are learning new stuff, man.
that.
I'd rather go with the term diagenesis is an after process. The primary process is lithification. Lithification is made up of what? Compaction and
Cementation.
cementation.
Alright.
Diagenesis is a post process that affects sedimentary rocks. So that's going to alter the poropen characteristics, poropen, porosity, permeability
Oh,
characteristics of the sedimentary rocks. Does that make sense?
yes, sir.
So sedimentary rocks are not formed by diagenesis.
Oh,
They are altered by diagenesis. Are you learning something new today?
yes, sir.
Alright. Or did I teach you that before?
No.
So where did you learn that from? You can fact check me if I'm right or wrong.
Alright.
Okay. Let's begin to round up.
Alright.
Okay. So we talked about the processes that would occur for the internal processes, right? What are the internal processes? Tell me.
Mantle convection
Battle convention that will lead to what?
that lead to the continental drift,
Continental drift that will lead to continental drift, yes.
and then
C
result
plus
in
spreading,
C plus spreading
the
and
tectonics, volcanoes,
mountains.
earthquakes,
Yeah.
all of that, right?
Yes, sir.
So then that will all accumulate into what the plate tectonics and divergent boundaries, convergent and transfer boundaries will form. Special processes that on your screen, isostatic readjustment, erosion, and then deposition. Okay? And this is sort of stuff I was trying to, tell you about
Yeah.
erosion, deposition, and uplift, right? Just because we want to attain that isostatic equilibrium. So if you look at the second diagram to the left, around page, I was like 18, right? what you would notice is that you've got a portion that has been eroded, and you've got three massive black arrows that are pointing upwards. And that is because the top has been eroded. So the rocks are trying to achieve that isostatic equilibrium. So there's going to be that uplift. Are you on there?
Yes,
If you're not looking at your phone and on the slide, I don't know what else you're looking at. Okay, slide 19. What can you see?
geologic cycle.
Geologic cycles. How many cycles do you have there?
3.
Hydrologic cycle,
Rock
rock
cycle,
cycle,
tectonic
tectonic
cycle.
cycle. All right.
Yes.
So the hydrologic cycle is driven by solar system or solar energy cycle, right? The tectonic cycle is driven by the internal heat engine that is derived from radioactivity. Okay? And all of this come into play to give us what? The rock cycle.
Hmm.
Does that make sense?
Yes,
Who doesn't relate? Who doesn't relate?
what did you say? Geological cycle.
For you to have the rock cycle, you must have both the internal heat engine and the external heat engine in place. Are we on the same page?
Yes,
Next slide. The role of exogenic and endogenic systems. Exogenic process drives hydrologic cycle. Did I say that in the last slide?
yes,
Both endogenic and exogenic processes contribute to what?
the rock
Did
cycle.
I say that in the last slide?
Yes,
Endogenic process drives what?
the tectonic cycle.
From home and dry. And these are all summary slides.
Hmm.
Okay? So you can see that in fact the earth is a system. Alright? It's a system because you have operational activities going on. You have sort of an input, right? You start from the far right, the left. Input, solar energy. Actions, energy, atmosphere, and water weather system. Okay? Output, exogenic process. You go from the right hand side, input, earth internal heat engine, action, plate tectonics, output, endogenic processes. You see how for both ends we get what? Last line.
Oof, hallelujah.
Processes and landscapes of the geologic cycle. Okay? Can you see that?
Yes. Oh, I hope you do 206. So I know which one time sitting
Can we see all of these processes on one slide right now?
Yeah,
Alright? What can you see?
can see
Hydrologic cycle on
that
top,
rainfall. Mhm.
rock cycle at the bottom right, left, yeah, and then tectonic cycle at the bottom right. And then you can see all the examples there.
Hmm.
Who doesn't understand this? The questions are going to be straightforward, right? The ability to tie in all of this understanding is what matters. I'm not looking for someone who can memorize the notes. I'm looking for someone who understands process. Do you understand?
Yes,
Did you learn anything today?
yes,
Who can summarize for me? What did we start off with at the end of the class? Number one, what did we summarize? You know what physical geology is about right now?
yes,
What did we move on to the next? Say again? Systems, right? And we said the earth is made up of what?
atmosphere,
Number one,
atmosphere, hydrosphere,
Biosphere and
biosphere, geosphere.
geosphere.
All right. What did we move on to then?
Earth interior, compositional layer.
Yes, and we said the earth is divided into what?
Composition.
Three, in terms of
Three.
composition.
Yeah.
The
In terms of
crust,
what?
composition.
Composition.
Right.
And
In terms of rheology is divided into what?
two.
So,
What is another name for rheology?
mechanical
All
layer,
right. What else did we move on to the next?
continental drift,
Okay.
and the theory of plate
And
tectonics.
so what drives all of that?
Internal
Internal.
Yes,
internal
internal
heat
heat
exchanger.
engines, right?
Yes, sir.
Another name for that is the endogenic process. Okay? And the endogenic process basically drives plate tectonics. Okay?
Mm-hmm.
What else do you move on to then?
Talk about the boundaries.
Plate tectonics, yeah, we talked about that. We talked about boundaries. We talked about surface processes that is driven by what?
External heat
What is
engine,
the driver?
the
The
sun.
energy from the sun.
Solar system. And I already told you how all of this precipitation work.
Yes,
When we say precipitation, we include what? Rain and
snow.
snow. Alright? When you talk about glacier, when you talk about glacier, you have snow that accumulates over time. I know I've not mentioned that, but it accumulates over time. When you talk about wind, how do winds form?
Yeah.
There's something. This man is telling me, I'm not trained by mind, but to progress.
Air passes. Oh, air something.
Formed by air person?
Air passes.
Yeah, but it doesn't form by air person. Now, what is wind? Moving air, right? Moving air. Did I teach you that?
Oh, movement from high pressure to low pressure.
Now, guess it. Have you guys done wind in this class before?
No.
Now, wind is moving air. You're absolutely right. But what would cause air to move? Pressure. Not just pressure. Pressure what?
Pressure difference.
Pressure differential.
Yeah.
Another one for that is pressure gradient. Wind will move from
High pressure to low pressure.
exactly. That's how you get wind to form. Alright?
Yeah.
Now, that pressure, right, is caused by what? The air is made up of particles. The more particles you get in a body of air, the more pressure you get. Alright? So, if you have this body of air here that's got more air particles, and a body of air over there that's got lesser air particles, the air will move from here to there. And then what you experience as a person is wind. That could be a driver for what? For what? Agent of erosion now. What are the agents of erosion?